Hi YouTube, how are we doing? So today I thought I'd start a little series. I've already posted one video from a prior channel that I worked on, but today I want to talk about how did we get from inches, meters to light years? How did mankind learn the size and scale of the universe? Now, there's honestly other people on YouTube who've done this, but I want to try to take it a little different direction. And I want to sort of go into a little more detail. So, the first part of our story is to describe how did we learn the size of the earth? You know, it could be something simple, it could be something obvious, but ultimately it was shadows. I'm here sitting, enjoying my little coffee. So, the person who first measured or attempted to calculate the circumference of the Earth was Eratosthenes, Eratosthenes, Greek philosopher, was living in Egypt, and he was a chief librarian of the Library of Alexandria. So it must have been before it was burned down. Now, any of you old enough to remember watching Cosmos? Uh, Carl Sagan actually covers this in one of the first seasons, one of the first episodes of the show. So basically, he lived in Alexandria, and the measurement of the Earth occurred because he knew about the shadows between Alexandria and the modern city of Aswan. So Eratosthenes measured the distance between the city of Alexandria and what was called the city of Syene, Syene, which is the modern city of Aswan. So, so he has these two cities. So what does he do? Well, he knew in Aswan that on the summer solstice, the sun was directly overhead. So if you look down a water well, you would see the sun in reflection. There would be no reflection. There would be actually not no reflection. There would be no shadows cast in the city of Aswan. But in Egypt, he could measure in the city of Alexandria, where he lived, that there was a minimum angle of about 7 degrees. So he hired these professional, hired these professional Vematists, Vematists, is people you can hire to calculate the distance between two locations on Earth. I'll gonna try to, if I can figure it out, interject little pictures of little devices they use to help them actually calculate. It's like a cart with some gearing on it to help them keep count. So, what did he learn? Well, let's see. So, in modern times, or using modern measurements, he calculated the distance between Alexandria and Aswan to be about 515 miles. I think the modern air distance is 525. I'll double check when I post this and edit this video. So, given that the Earth's a sphere, they assume the Earth was a perfect sphere. It's not, it's a little ellipsoid. It's fatter around the circumference than the north-south pole due to the centripetal acceleration of mass. So, what did he do? He estimated that he took the distance from Egypt, from Alexandria to Aswan, and computed that the meridian has a total distance of 252,000 stadia. The stadia is about 150 meters, 160 meters. So it's estimated. We don't know exactly the true distance of a stadia. It's between 150 and 160. And his answer is within 2% to 0.5%. I'll post a link and a clip of the wiki article. So that's how we get from not knowing the size of the Earth to the size of the Earth. So, cast shadow, shadow's 7 degrees. He estimated that there are about 50 times the distance to go around, 360 degrees. And it's, if you divide 360 by 7, it's more like 51.3 or something like that. But he used 50 as an estimate, and he still got to within about 2%. So that is how we calculated the size of the Earth. You've had hire someone, figure out the distance between the two cities, and then say, hey, the Earth's round. This is how far 7 degrees is, so that's 360 degrees. So then that takes us to how far are we from the moon? So that's another clip. Now the distance to the moon is a little different. So the distance to the moon actually involves a couple of different techniques, but the one that I think gave the best result, or gave an easy result to attain, is measuring the speed at which the moon crosses the Earth's shadow. So you can say, how big is the shadow across the sky? How many degrees is that shadow? So use the background stars to help you find where the shadow is, right? Based on where the moon intersects. And then you time how long it takes for the moon to cross that shadow, right? They didn't know the Earth actually went around the sun. Well, some people did, but they have no idea how fast the Earth actually moves. So if you calculate how long it takes for the moon to cross Earth's shadow, and you know how big the shadow is against the background sky, so you assume that there's a celestial sphere that goes 360 degrees around for the Earth's orbit, you can compute how far away the moon is based on the Earth's radius. If I can find some calculations, I'll post them. Don't count on it. This is just a very brief intro and talk. I don't want the video to be too technical or to be too long. So from there, you see we have now the distance to the moon. So that's a little easy. So then you need to know the relationship to the distance of the planets. Well, Mercury and Venus are pretty easy. I just realized I was on the wrong mic. So hopefully this part gets a little better. I don't want to have to try to repeat the first half, but it's only about 7 or 8 minutes so far. So let's continue. Where were we? So we needed to now figure out the size of the solar system. And that's a little easier, not by much. Actually, the inner planets were easy. The outer planets were extremely difficult. And that's because the inner planets never deviated far from the sun. So they knew the inner planets had to be within the Earth's orbit, assuming you accepted the Copernican model of the solar system. And because the planets never deviate far from the sun, if you do a little geometry and you draw tangents, so the maximum deflection would be the tangent to a circle that's the circumference of each planetary orbit. And if you assume the sun-Earth distance to be 1, and you take the angle, the sine of that angle, is it? Yeah, the sine of the angle will give you the distance from the sun to the planet. So you get Mercury and you get Venus. So, yeah. So that was Mercury and Venus. That's very easy. Mars, which is I discuss on the other clip that I have, Mars actually took the work of two people. It was pretty much determined by Johannes Kepler, but he had to kind of like steal the data from Tycho Brahe. So Kepler worked for Tycho Brahe and did some observations for him. And upon his death, I believe he thought he was entitled to the data. So upon Brahe's death, he kind of like stole the data. And there was a lot of data. I mean, it's like they say, everything, data is everything. Data is money, data is gold. So what did Kepler do? So Kepler did some geometric calculations of Mars's orbit. So I think Mars's year is like 444 days. I'll put an overlay if I'm incorrect. So in the video that I posted prior, I'll leave a link, you can calculate not only the distance, I believe, but he figured out the distance another way. So let's talk about that first. Let's not deviate. So let's say you wanted to calculate the distance from Earth to Mars. Well, you know how long Earth takes to go across the sky, and you know how long Mars takes to orbit, right? So Earth traverses, the way you do Earth is you find out where the sun is against the background sky. And it takes the sun about 365 days to return to the same spot in the background sky. So you know how fast the Earth traverses the sky. It's about 365 days, it's 360 degrees, so it's about 1 degree a day. So then you look at it and say, hey, we know how long it takes Mars to go across the sky. You know, how long does it take Mars to return to the same spot in background sky? So then you're like, okay, we can use this. And how do we use this? So how do you do this? So you wait for a period in Mars's orbit where it goes retrograde. And when it goes retrograde, when it enters retrograde, you can determine how long it takes for Mars to return to the same spot against the background sky, right? So you find Mars, find a sky, you find a star, You wait for it to go into retrograde, and then you determine how many days it takes for Mars to return. And you say, well, Earth moved so many degrees across the sky. So I'll try to put a little graphic overlay. So you have two parallel lines. One is Earth and Mars and a background star on day one. And then there's another parallel line, Earth, Mars, and a same background sky, but with the Earth and Mars further along in their orbit. So you do a little geometry, sun to the Earth is 1. You have an angle, you do some trig, and then you can determine the Earth-Mars distance. And then knowing Earth-Mars, you know what the Sun-Mars distance is with respect to the Earth. So right now, everything is based on the orbit of the Earth, the radius of the Sun-Earth distance, which will eventually be called 1 astronomical unit. So what do we do from there? Now you're like, okay, so Kepler got the distance, but he needs to get the shapes of the orbits. And what you do is you take a day and you find out where Mars is in the sky. And you know how many days a Mars year is. So you say, okay, where's the Earth, Sun, and Mars relationship that many days later? So you look up in your tables and you say, well, the sun is in this part of the sky, which would put the Earth in this part of the orbit. And then you do it a couple of more times. And then you have like 4, 5, 6 data points. And then you look at another day, maybe 1, 2 days later. I want to point out that 3 blue, 1 brown, I think. Yeah. I had a great video on this, and I'll leave a link to it. But so if you do it again, you get a bunch of other data points. And if you keep doing it, you get a bunch of other data points. And if you pick enough days to plot out where Mars is, you can pretty much determine the shape of the Earth's orbit. And then how many days it take for it to go from one point to another point. So that's basically how Kepler got his other laws. Planets orbit from a point on an ellipse, and they cover equal areas in equal times, meaning they speed up when they're closer to the sun and they slow down when they're further away. And he got the relationship of the orbits. If I remember correctly, it's radius cubed is proportional to period square. So I know Jupiter is about 5 AU, and it's 125 is 5 cubed. And then you take the square root and it comes out to like 14 or 13 or some crazy number like that. So yeah. So now we have the size of the solar system in relationship to the Earth's sun distance. So we know the ratios of the distances. We don't know the exact distance. And the exact distance actually comes down to the transit of Venus. Everyone, well, if you're a science person, you probably know this one, but it comes down to the transit of Venus. expeditions were sent all over the planet to measure how long it takes for Venus to traverse the sun. They assume a certain angular distance, so all of the measurements were done in angles. So the sun is about 1 degree across the sky, and you time how long it takes Venus to cross the surface of the sun. And they took different measurements. When it entered, when it first touched the corona, the front side, when the back side of Venus touches the corona, touches the surface, the edge of the sun, and then 2 more data points at the end. And these were all timed. Now, why did they have to measure the time it takes Venus to traverse the sun? Because they needed to measure the chord length. And if you know the chord length of a circle, and you do some trigonometry, you do some geometric calculations, you can determine the distance from the chord to the center of the circle, right? So the longest chord, the diameter, goes through the center. And as you move away from the surface, you move away from the center, you get distance from the center related to the chord length. But, I'm just babbling a little bit. Forgive me. So if you know the chord length of different observation points, okay, you get parallax. You get a parallax shift from different observers. So a northern hemisphere observer will see Venus below a southern observer. So you draw a line, you have the person at, let's say, the North Pole sees Venus, and from his perspective, Venus is below the center of the sun. And if you're on the southern hemisphere, if you're in the South Pole, and you look at Venus against the sun, you're going to see the sun above the center. Let's say it's extremely exaggerated, but it's something like that, right? It's not going to be exactly above, but one's going to be above, one's going to be below. That's the important part. And if you measure the chord lengths, because you can't really measure the distance Venus is from the center of the sun. That's almost impossible to measure with the instruments at the time. So if you measure different chord lengths, you have 2 different measurements for the distance to the center. If you have 2 different measurements for the distance to the center, then you know what the difference is between the 2 chord lengths, right? So if one chord length is 1 and one chord length is 0.7, then the distance between the 2 chords is 0.3, as an mathematical example. So once you have that, you now have the angle that you need, the parallax angle. Okay. Once you have that, you have the distances of all the observers, and you can triangulate the distance to Venus in terms of the proportion to the Earth distance. Okay? And you have the distance in a unit you can measure, which is miles, right? So you have 2 points on the sphere. It's easy to find the distance between 2 points in a sphere. Okay? And you have your parallax angle, which is the angle, it's the angle made from observer to Venus back to observer. So observer A, Venus, observer B. So it's that angle. So we call it O1 V O2. Okay? Once we got that, we discovered that Venus is about 0.7 of the distance from the Earth to the sun. And converting it into miles, we discovered that the sun-Earth distance is about, on average, 93 million miles. And knowing that the Earth-Sun distance is 93 million miles, we now have a measure for the circumference of the Earth's orbit and its diameter. And once you have the diameter, it's 186 million miles, right? 93 times 2. You can now apply parallax triangulation against background nearby stars. And that's going to be in the next section. Bye now.